Okay, thank you. I'm first sharing my slides to check that we are okay. So can you see now my slides and hear my voice also?
Yes.
Okay. Okay, so thank you very much for this opportunity to give the keynote speech here in this conference. So my name is Mikko Kolaman, and I'm a professor of environmental informatics and modeling at the University of Eastern Finland in Kuopio, which is located in Eastern Finland. So I was actually in 2017 in Krasnoyarsk in this same conference physically, and that time I was talking more about kind of biology related modeling, which we are doing and have been doing in our research group. But today our idea is to talk about a little bit different things. So basically about the general trend of artificial intelligence and digital twins, which is, I think, shaping the modeling community at the moment. This is combined with examples from the energy sector, which is one of our main research areas in our research group. And so this presentation will be twofold. I will first give some overall ideas about this AI trend, and then Christina Brester, who is working in our research group, will continue with some examples that will then make these ideas perhaps more concrete, or at least show what we are trying to do based on this motivation that I'm trying to give in the first part of this presentation. So shortly something about myself, something about AI and its current status, some analysis of the weak points, and then moving to digital twins. And then I think what is important also try to see what is the relationship between digital twins and AI-based solutions, and how we could combine these. Also some recommendations what could be done in the future, and at least what we are going to do about this. And then Christina will continue from that with 3 examples that will try to enlighten the work we are doing in this sector. So I started my career in the private software industry, about 5 years there as a system analyst and chief software engineer. But then in the 90s, I moved to academic work. I studied some biotechnology and also done my PhD at the quite late stage when I was actually already more than 30 years old. And but from that work, what the conclusion was that we were able to create the research group of environmental informatics in our university, and also were able to get the professorship for that particular subject. So for about 20 years, our research group has been carrying on mostly industry-related project using artificial intelligence-based methods to solve the problems that are related to environment in a quite large context. A couple of years ago, I was also working half a year period in a startup company that was trying to put AI methods into practice in the companies. And unfortunately, that didn't fly, so I returned to university just before the COVID epidemic started, so in March last year. Also, I had the honor to be the chair of the IWMMA 2009 conference here in Kuopio. So that's shortly about myself. And now I try to move to give some of the ideas how I see the artificial intelligence wave at the moment. So I think during the last 5-10 years, the main characteristics I think is that the machine learning, which is perhaps the main or most important part of artificial intelligence, it has become accessible with the platforms and software libraries which have been provided by the big players. And I think the characteristics are that actually in some cases you don't need the coding at all, or at least not coding of the algorithms themselves. There are some automated model development and also integration in many respects, like to the data and also to the user interfaces. Also, the cloud information means that you don't have to set up your own server environment. Also, there's a number of new methods like deep neural networks. So all in all, I would say that there's more focus on solving the practical problems and not developing the algorithms themselves. So what do we gain with this progress? It's possible to tackle problems that we're unable to do in the past. We don't need to know the logic if we have enough data. And also, especially because of this late progress, there's ease of application. You can get solutions by clicking the button. So in a way, AI has become part of the mainstream software engineering. And the development to production has been streamlined a lot. And I think this is a very good progress which is connected to the information society. So from data to information and knowledge. But there are some weak points which I try to list here from our perspective, from the work that we have been doing. So first, I would say that AI is mostly interpolation instead of extrapolation. So the data that you have, it limits what you can do. You can mostly work with just the problem areas where you have data collected. Also, most real-world data sets are full of errors, missing values, outliers, missing metadata. And also, I think that despite of all this automation and streamlining, the developer still needs to be quite experienced. So to be kind of data scientists, not just data engineering. And I think model validation is an important example of this. I think it's usually underrepresented in the work. So what we could do better with our AI solutions. The data curation could be more automated, outliers, missing data handling. The second point is about metadata. We have seen in some industrial projects that there might be a lot of data, but not enough metadata, or at least not metadata in a format that makes the data useful. So in the worst case, you have a variable, but you don't know what it represents. So we need tools for discovering the dependencies and even causality-like issues in the data. And as already said, model validation needs better tools, both graphical and numerical performance indicators. So this is perhaps just a quite limited list, but that comes from our own projects and research work. If we then move to digital twins, which is nowadays discussed a lot, so what they are and what they are not. I will first give some examples what they are not. So if you just have IoT data, that's not the digital twin. Or if you have a trained machine learning model, that's not the digital twin. Or some people say that when have 3D picture or layout of a building or factory, that's a digital twin. But I wouldn't call those digital twins. My definition for digital twin is that we need both the model and representation. So model is the description of the entities and their relationships in your process. And then we have the representations, which nowadays quite often is 3D model. but basically we need this both, and I think for many people it comes as a news that you really need that. Actually the modeling is the central of the digital twin. So what is the relationship between these two concepts, digital twins and AI? So basically both can be used to capture the behavior of some process we are investigating. We can predict new values based on them. But as already said before, the data-based AI model is only valid for the area where you have the collected data. On the other hand, the digital twin model can be used to ask what-if questions. So we can go beyond the data that we have. One idea that many people have lately discussed is that if we have the digital twin model, then we can use that to produce data which can be used to train an AI model. I think this is a kind of sound logic, but the problem here is that the bottleneck is the original construction of the digital twin model. It's not enough to have the IoT data. You need to describe the entities you are using and the relationships. Also, one thing that has been investigated in our research and also in one company which I'm cooperating with is kind of hybrid modeling, where you combine digital twin models with the AI models. So in some parts where you have very good data, you can create a machine learning model and then plug in that into the digital twin. So how could we combine these? This is kind of simplified step-by-step process with a little bit illustration to show the entities that we need to deal with, perhaps in the cloud environment. So as before, you need to collect your data or get it somewhere. You need to curate the data. Then you need to plan and create your digital twin model. And that is perhaps the hardest part, perhaps at the moment. After you have the model, comes the phase where you need both the data and the model, so calibration. You probably have some free parameters in your digital twin model, so you can use the data to calibrate it. And then you can use that calibrated digital twin model to optimize the process or reply to what-if questions. And then perhaps optionally create data for training the AI models. So to get more concrete and towards Christina's part of this presentation, here's one example of an energy system, which in this case is one family house. We have been using this as a kind of model system in several of our research projects. So what we have here is different subsystems: solar panels, air heat pumps, ventilation with energy recovery. There's usually some basic heating, which in this case is direct electrical heating from the floors. It could be, of course, ground source pump also. We have the house and its characteristics, which has to be remembered. It has certain buffering capacity. If the temperature outside drops quickly, it doesn't reflect to the heating need at the same hour. It takes some time because the material of the house has some buffering capacity. Then we have some external players like electricity exchange hourly pricing. So at least in the Northern Europe nowadays, we have the tomorrow's hourly prices available the previous afternoon. So this afternoon we will get a fixed price for using electricity for tomorrow for each hour, and that can be used as a starting point for optimization. Also lately there are plug-in hybrid electrical vehicles, but also electrical vehicles which are also shaping this modeling. And so to start to make a digital twin model for that, we would have to define these concepts and also the relationships between them. And to give something concrete, how to do this, at the moment, I'm evaluating a tool called AnyLogic. So this is not a commercial advertisement, but just to give you an idea if you like to look what to use for this type of modeling. So AnyLogic seems to include different types of modeling: discrete, event, agent-based, and system dynamics modeling, and combinations with this. You can also export this to the cloud environment. A lot of examples available, and also a free version for trial usage. So this is, I think, a very good environment to have a look. Well, it's Java based, so some of you might dislike that. So, but I think that should not be a problem. Then some recommendations. So what should be investigated? So one thing I already mentioned, how to use the digital twin model to produce data to train the AI models. That's one interesting point. How much of the work for constructing the digital twins could be automated? Could it be even possible to construct it from the data kind of automatically? The calibration process, when we have the digital twin model and the data, how can it be automated? How to transfer models between different tools. The different evaluation algorithms are needed for the calibration and optimization. There's work to be done there. Then there's this integration to the representation of the models, like laser scanning. And then, of course, doing different kinds of real-world examples to learn about this. And now I will give the floor to Christina, who will continue from this and try to exemplify these ideas. So Christina, please go ahead.
Thanks, Mikko. Hello, everyone. Okay, let me share my screen.
Okay, we can see it.
Very good. Thanks. Okay, before I start with our 3 examples, I would like to make a quick remark. All the results I present later were obtained on the test data. So everything I will give you were obtained to estimate the generalization error estimates for the presented models. And within these 3 examples, we have studies that are devoted to, first of all, network or microgrid level examples, and second of all, some examples for the household level modeling. Okay, and now the first example. Probably on this slide, you can clearly see our motivation, why we really need to predict weather-related faults in the network. So, for example, last year in Finland, after severe storms, thousands of households were left without electricity. And at the same time, for companies responsible for power supply, that means financial losses. But if we were able to predict this weather-related faults based on the data, that would be possible to warn these companies in advance, and they would be able to reserve some needed workforce so that the repair crew would be dispatched without delay, and all these outages wouldn't affect customer satisfaction at all. So in our first study, we had data from one of the Finnish distribution system operators. So DSO stands for distribution system operator, Elenia. In this figure, you can see the network of its substations. And for the period from 2011 up to 2013, the data faults were recorded by Elenia, and we received this data. Unfortunately, most of the faults were not labeled, so they were not kind of classified, and most of those are unidentified. Sorry, some of them are wind-related or snow-related faults, and the idea was to predict faults, the number of faults in the network. First of all, in the whole network at the network level, knowing the weather conditions. And as inputs for this model, we used weather predictors like temperature, humidity, wind, everything you see in the table on the slide, and also time variables. They were month of the year and hour of the day. Then we applied transformations, sine and cosine, to produce cyclic variables. Yeah, actually, we published a paper devoted to this study. And in this paper, we tested different neural networks, including recurrent neural networks, simple ones, and also LSTM. And at the same time, we tested also MLP. And we figured out that MLP outperformed recurrent neural networks. Probably the reason of that was because the model actually didn't need very long history of previous weather observations to make a decision about the number of faults, because in the data, in the meteorological observations, we had cumulative numbers now. And knowing that, probably we don't need all the previous history. But still, MLP took into account 6 previous hours prior to the point of prediction. And it was able to predict high peaks. And this is quite important because in the first figure, you can see MLP. It was trained without any oversampling, using training data from previous years, from 2011 and 2012. So, and this model wasn't able to predict these rare high peaks at all. The problem was that these events, these high peaks, at the same time, they were, of course, of special interest rather than these usual ordinary situations with little number of faults. But we were really interested in these peaks. And to make the model predict those high peaks, we needed to apply oversampling. Yes, this is a very simple solution, but still it worked successfully. So, and you can see, for example, if we compare index of agreement, this is a metric, its maximal value is 1. So the higher index of agreement, the better. So if we compare index of agreement from the first figure and index of agreement from the second figure that corresponds to MLP with oversampling, yeah, we can see that the second model, it's more or less acceptable, yeah, with 0.78. Yeah, but then we also repeated a similar experiment for wind-specific faults. We used the same MLP architecture, and again, we were able to get quite good results already for wind-specific faults. So in the first experiment, what I just described, we predicted faults for the whole network, but then we had a joint study with another Finnish university. And the idea was to predict these faults locally, to introduce some clusters, local clusters, and predict faults daily in each cluster. So that the results of this modeling were used later by our colleagues in their own study devoted to optimal resource scheduling. So, and for some clusters, we were able to reach quite high accuracy, like 78 or 75. All in all, this example illustrates that data-driven models are able to evaluate the number of faults in the network and locally in the microgrid. And these models are helpful to simulate and to test different scenarios. For example, if we investigate microgrid resilience or optimal scheduling of battery charging, optimal personal scheduling under different weather conditions. And speaking of which, weather conditions and weather in general is a very important ingredient in our second study, in which the second study is devoted to day-ahead solar PV output forecasting. So PV stands for photovoltaic. Basically, we studied solar panels and we tried to predict the number of energy generated by solar panels in 3 different sites in Eastern Finland, two of which were in Kuopio and one a bit far away from Kuopio in the place called Vuorela. So there are 2 conventional approaches to make predictions to predict day-ahead solar PV outcome. The first one is physics-based and the second one data-driven. For the physics-based approach, you always need to know precisely characteristics of solar panels, for example, slope, angle, azimuth angle, and some other physical characteristics of the solar panel. And also, there is another problem that if, for instance, shading takes place, you would need to apply some site-specific post-processing of the model outcome, because nearby trees or buildings really disturb the model predictions. So alternatively, there are data-driven models, but to train those, we need a lot of data. And there is one big problem is that conventionally, to train data-driven models to produce day-ahead solar PV forecast, we need weather forecast. And the data-driven models are also trained on weather forecast, which means that we would need to have a lot of historical data, historical weather forecast. But I'll continue here. But data are much more difficult to get compared to historical weather observations. For example, in the website of the Finnish Meteorological Institute, you can easily go there and obtain historical weather observations. But what about weather forecast? Okay, probably you can get only some recent weather forecasts from this site. And therefore, in the literature, the data availability is supposed to be the biggest problem to train the model that can produce day-ahead solar PV forecast. Therefore, in our second study, we were interested to check what happens if we switch from this baseline scenario when they use historical weather forecasts to train the model and then to test the model, when we switch to the alternative scenario, when we first use historical weather observations like real weather to train the model, and then to simulate the model operational use, we switch to weather forecast. So, and here on this slide, you can see the results of these experiments. Again, we use MLP, and you can see the results we obtained from the baseline scenario and from the alternative scenario, and also at the same time, we provide the results of the physical model. The physical model outcome was provided by the Finnish Meteorological Institute. They're using this model in their studies. So I would like to comment probably the first figure, because we know that for the first site, this Vuorela site, shading is a problem. And that's why the physical model, these purplish dots correspond to the physical model. They kind of show the overestimation made by the physical model. Then if we compare, for instance, index of agreement and mean absolute error achieved by the MLP model in the alternative approach, yes, okay, it's slightly worse than metrics achieved in the baseline scenario, but still, if we don't have historical weather forecast, this is the way to go. This is a very good opportunity to train first your model on the observational data, and then even when we switch from observational data to weather forecast in the vector of inputs, model demonstrates quite high performance compared to the physical model. What we can see for all these three sites. Yeah. And here, kind of more detailed visualization of the forecast. And again, for the Worrell side, this overestimation made by the physical model is clearly seen. Okay, so probably again, quite general conclusion why we really need to do this, to build this model to predict day ahead solar PV forecast, is just because we need to integrate this solar PV outcome into the overall household energy consumption profile, then to apply different control actions to optimize these control actions. And especially, it's important, especially because of day ahead trading of electricity in Europe. Yeah, and the last but not the least study made by my colleague, it's about, again, day ahead forecast, but now it's about the electricity consumption for one personal house. So the first important point in this study is that the overall electricity consumption might be divided into two parts. The first type of loads are temperature-dependent loads, so-called thermal loads, and the second type of loads are behavioral, they're like time-dependent loads. And first, the idea was to split from, let's call that signal from all electricity consumption. We need to extract thermal loads and then behavioral loads also to model them separately. Because, yeah, I can tell you that later. So this is kind of the illustration what we get when we split. Okay, we know that thermal loads are usually linearly dependent on the temperature. Therefore, in this part of modeling, we built quite simple linear model to extract this thermal loads. And you can see, for example, this is the profile that corresponds to the overall consumption. And then here in the second plot, we can see this thermal loads. They are quite similar to, so the changes that we can see in the second plot correspond to also changes, like daily changes in the temperature and the outdoor temperature, whereas these time-dependent loads, they have quite different character. So now we have this temperature-dependent loads and behavioral loads, and we modeled those two loads separately. There are quite good physical models, systems of differential equations to describe this thermal loads and thermal profile, let's say, of the house. And in this study, we used one of those, but here the second important point of the study, and it's about the kind of novel approach when we use the physical model using neural networks. So every equation was transformed using numerical differentiation to some form, like similar to what we have here on the slide. And then after this transformation, it was possible to build a neural network with feedbacks to represent this physical model. And now we were able to use all the contemporary tools, existing tools to train neural networks like Adam Optimizer or whatever you're using in Keras, TensorFlow, and so on. So then we trained this model, and one good point here is that in this model takes into account also control actions. And using this model, it's possible to test, simulate different control actions and to investigate response to different control actions. For instance, we can check different scenarios. For example, we know now it's pretty warm inside the house and you don't need to warm up it now because prices are very high. And so what happens if we apply these kind of control actions now? We turn off heating and then we turn it on later, and we can check the temperature inside the house following these control actions. Yeah, so, and this scatter plot also illustrates kind of the model performance. Temperature dependent loads mean this extracted kind of true loads, and then here we have physical model outputs, kind of predictions of this model. And then, so first we modeled this temperature dependent loads with physical model, and the remaining part, this behavioral loads, time dependent loads, they were modeled using data-driven approach called stacked boosters network. Actually, this approach was proposed by our colleagues from VTT Technical Research Center of Finland. And here you can see the overall forecast. So the overall energy consumption evaluation for one house. Yeah, and in this study, we presented a hybrid approach that combined a physical model to predict thermal loads and data-driven model to predict this behavioral, the remaining part of loads. And using the physical model, we can easily test different control actions and check different scenarios, and also probably to optimize somehow control actions for the next day, because we know already prices for the electricity for the next day. And here probably I would like to welcome back Mikko. Thanks for listening.
Okay, so I hope that these examples illustrate what kind of work we are doing here in Kuopio, and also perhaps enable to see why we need both data-based AI models and physical models in this new world of digital twins and creating them. So here are my contact details in case you would like to cooperate for this kind of work, either in this energy field, or we are also working with some aquatic and health-related modeling topics, or if you are even interested to come to Kuopio at some point to work here, so please contact me. And I think that is all for this presentation. If there are now some questions, perhaps we could try to answer those with Christina.
Okay, thank you very much for presentation, Mikko, Christina. Dear colleagues, please ask your questions. Okay, maybe I'll start. Could you specify again, why do you need two kinds of models? If we have normal mathematical models from physical reasons, and at the same time you need neural networks which present the same physical models.
Okay, probably this is a question to me about the last study.
Okay, it doesn't matter.
I don't know. Okay. Yeah, probably it was just an idea to use all the existing tools to train the physical model, because from our experience, there are often some obstacles to tune parameters of the physical model, and it was just just an idea to explore the possibilities of existing tools because they are quite effective in training neural networks. And we thought, okay, maybe if we can represent the physical model as a neural network with feedbacks, and we know that these tools are effective in training neural networks, probably we can test the final model, how it's trained by these existing tools. But at the same time, now we also aim to compare, for instance, optimization algorithms for tuning parameters, the same physical model, global search. And we're planning to contrast the results obtained by this approach, just global optimization, and the one which is used by Keras when we train neural networks.
Okay, so if I can continue at the general level, I would like to point out that the main strength of the physical models is that you can extrapolate. So basically in many processes, you might have only data from the process behavior, which is quite normal or close to normal, and you might not be able to run the factory into a fault situation on purpose. So if you have a physics-based kind of digital twin model, you can at least try to survey those different, let's say, error states using that model. With the data-based model, you cannot do it if you don't have the data for those fault situations. On the other hand, like this solar panel example showed, in some cases the physical model can be quite misleading. So in that case, we need the data-based model because it can kind of fit into the local conditions if you have the data. And I can see a role for both of those, and also as I in my presentation suggested, and as actually one of our cooperators, a company is doing, they are building a digital twin model where they have both physics part and they have data-based part. So they have machine learning and they have physics model there at the same time in the same digital twin model. So I think in this kind of research work, it's important to keep both these alternatives and try to compare how they behave in different situations and get kind of understanding what are the weak points, what are the problems, what are the strong points of both of these modeling types.
Okay, thank you. And more technical, let me say, question. You show that there is a system of differential equation as physical models. Why do you use this system of differential equations instead of solution of this system?
Christina, can you get that?
Probably
okay,
first we'd like to identify the system, identify parameters of the system, because we don't know some of its parameters and we have observational data, and based on the observational data, we would like to identify the whole system.
Yeah, but in any case, you need at least numerical solution of this system of differential equation to model the process, no?
Yeah, but we have, for example, this power was that measurements in time, and this system kind of, the solution of the system would be also then some kind of estimation or description of the power in time.
Yes, if something in parameters has been changed, you should put this changed parameter again in the equation system.
You're right.
And solve this system again, numerically.
Yeah, but the system it describes every house. So like some thermal properties of the house, and there is not much possibility that this thermal properties would be changed.
I mean that if you will solve analytically at once the system, you will have instead of system later just the formula of functions that can be easier calculated, not numerical process each time.
Well, yes, probably, but this is something that we would need to do at the later stage. First, we needed to identify this weight coefficients anyway, or maybe I just cannot get the point here.
Maybe I don't understand this fully, but basically the model of equations is a general model for any house. And then it has some free parameters, like each house has its own thermal capacity. It has different thickness of the walls and so on. So basically in different houses, if you don't heat at the time, the number of hours needed to have a 1 degree drop inside the house, it is different. So we are first fitting these parameters for each individual house. So after that, it will be an individual model for each of the house. Yeah.
Do you mean that analytical solution of this system can be completely different for different houses?
I think so.
Not difference. Yeah. Difference is not only in parameters, but also in configuration of function itself. Yeah. I mean that for one, for example, house, solution is f at t is equal to sine t, but for another, f at t is equal to exponent of t squared.
Okay, so they would have a different time behavior in a way.
Okay, I see, I understand, thank you.
And also, like initial conditions would affect the result heavily.
Okay, I see, I understand, thank you. Dear colleagues, please ask your questions. Okay, it seems our presenters were absolutely clearly to explain everything except myself. I'm only who did not understand at least something. Okay, thank you very much for your presentation. Thank you very much for answering of my question. And please join us in the next hours of our conference.